Start the presentation.
Okay.
Okay.
If you're ready, we can.
Yeah. Okay. Yeah. Dear my colleagues, welcome to the presentation. Today we are going to follow an interesting presentation. This presentation will be about how to do mining in space. Professor ROSTAMI executes some project which is supported by National Aeronautics and Space Administration, briefly NASA, you know. Therefore, he is very experienced in space mining. I hope the presentation will be useful for us and give some ideas, and it will broaden our horizons. Professor, I would like to briefly introduce Professor ROSTAMI. Just a minute, yeah. Professor ROSTAMI is the head and Alacer Gold Endowment Chair and Director of the Excavation Engineering and Earth Mechanics Institute of the Department of Mining Engineering at Colorado School of Mines. He has BSc in Mining Engineering from University of Tehran, Iran, and his Master Science and PhD in Mining Engineering in 1992 and 97 from Colorado School of Mines, respectively. He has been a faculty at University of Tehran from 1988 through 2002, and full-time consultant with major EA companies from 2002 till 2007, when he joined the Pennsylvania State University as Central Chair of Career Development in Mining. He has over 28 years of experience in design, management, research, and teaching in the field of mining, tunneling, and underground construction. Dr. ROSTAMI is registered professional engineering in Maryland, Pennsylvania, and Virginia. He has published over 90 peer-reviewed journal publications and 150 conference papers and many technical reports. He is a member of SME, SE, Army, ISE, and TRB AFF 60 Tunneling Committee. He is the editor-in-chief of the Tunneling and Underground Space Technology, member of editorial board of several rock mechanics and mining journals. He is also of the executive committee of International Tunneling Association, or ITA. Dr. ROSTAMI was named the recipient 2014 of the Pittsburgh Coal Mining Institute of America 2014 Stephen McCann Memorial Educational Excellence Award. Professor ROSTAMI, please go ahead. You have your word. Thank you for this presentation.
Absolutely. Thank you for the kind introduction. Good evening, everyone. I hope you're all doing okay. It's strange times with, spending a lot of time at home, working with COVID-19 threat outside. I hope this presentation would be interesting to you. It's about, what's happening in the sphere of space mining and what are the opportunities and challenges. So the view graph that you see up on the screen, especially this is a sort of a cartoon that was made back in 1990 at Colorado School of Mines, essentially making a joke of mining in the space with a pick and going down in a tunnel. So before I start the presentation, I just wanted to let everybody know that Colorado School of Mines, as of 2 years ago, is offering master and PhD in space resources and space mining. So for those who are interested, they can actually look it up. We have over 100 graduate students right now from all over the world. The program is online. You can participate. So this is the general outline of my presentation. We'll talk about why space mining, what are we going to mine, where are we going to actually build or mine, what are the timelines? Then we'll very briefly talk about lunar, asteroid, and Mars mining. And then if I have time, I will discuss some of the ongoing research that we have been involved with for the past few years. So, of course, space has been fascinating. You know, we've tried in past last century to get access to space, first with flying and then flying out of the atmosphere, and ultimately, you know, going to the moon and trying to essentially have a permanent presence in space. And at this stage, we are talking about going deep space. Now, the reason that we need to talk about deep space is that for any deep space mission, we have to actually have some sort of a system to exploit the resources in the outer space. It's not feasible to take material from Earth over to the outer space and use it. It's very expensive and very difficult. So we have to use the material in situ. So therefore, you see the term in situ resource utilization, or ISRU, being used very often with the people that are discussing deep space missions. Of course, at this stage, the cost of liftoff from the Earth is very, very expensive. And there has been some changes in recent years, especially with SpaceX trying to reduce that cost by 10 times. Of course, if we want to discuss future space travels, then again, we need the resources out there. So what are we looking for? We are looking for primarily oxygen and hydrogen, which, of course, if you get water, you have both of them. So the first target, as we'll discuss later a little bit more, is water. That's what we are shooting for. And of course, there are some other minerals and metals that we can mine and bring back, but in short term, nothing is going to come back to Earth. It's primarily the issue of mining the material for essentially supporting the space missions. And the reason that it is interesting and very hot topic right now is that US is planning to go back to moon by 2024. And as of now, they're planning to have a base, some sort of a base on the moon by 2028. And of course, there has been a lot of exploration missions going to the Mars. And again, there are discussions about actually sending men to the Mars. In addition to all of this, there is a huge interest in commercial application of the space. And there are, right now, some of the companies are purchasing, they're asking for water to be delivered to the satellites as a fuel in lower Earth orbit or geostatic or Earth orbit to essentially operate their satellites beyond their the life. And of course, I'm sure you may have seen it in the news that there are some billionaires that are now trying to get into the space business, and like Elon Musk, Branson, and Jeff Bezos that are spending literally multi-billion dollars to get access to space for the variety of reasons that I mentioned. But one thing that's very interesting, a study that was done in 2015 by ULA, United Launch Alliance. The United Launch Alliance is a company that actually manages the US satellite launches. They did a study of what they call cislunar marketplace, or essentially out of space activities. And their anticipation is that in about 5 years, which is about right now, you might have 5 people permanently living in outer space and about $300 billion per year worth of activities. Actually, that was the time, and then now, maybe that number has increased to 20 and then 500 billion. And the anticipation is that in 15 to 30 years, we might have, much more presence in the space. And if you think about a 30-year outlook, the space business between Earth and moon and the gateway going to Mars, all the satellites and all of that, could be $2.7 trillion per year business, which is huge. And they're anticipating that at that time we will have around 1,000 people living, excuse me, in outer space. So to really summarize the issue of what's the in the core of the space mining is that, as I said, the cost of liftoff and sending material up to the Earth is very high. Let's say for a kilo or 1 liter of water on the Earth, it doesn't cost much. It's really near free, right? If you take the same water into lower Earth orbit, then it would be around $4,000, to the geostat orbit about $8,000, to the gateway over to the moon, it would be around $18,000, and so on and so forth. If you take that same 1 kilo of water to the surface of the moon, with today's technologies, $35,000 per kilogram. So you can imagine, as you go further out, that same 1 kilogram is going to cost a lot more. However, the studies that has been done shows that if we can mine water on the moon at $500 per kilo, and even, of course, we can use it on the moon, bring it back to the gateway, and bring it back to the Earth orbit. Even if we bring back water from moon to Earth orbit, it's going to be cheaper if we can produce it at $500 a kilogram. As you can imagine, there is a economic case here for going to the moon. So when we talk about going to the moon and mining water, where, of course, is the question. In the lunar poles, the both north and south pole of the moon, there are actually incidents and evidence of water. Of course, there are discussions about Mars, and there are water and methane on Mars, and there are some other deposits as well as CO2. And asteroids is an interesting prospect, that they can be made of anything from ice to minerals to metals to stone. So these are the typical material that we're thinking about, mining. So if you look at the moon, and especially for water exploration, there has been a lot of exploration and essentially trying to identify the sources of water, hydrogen and oxygen on the moon. This is a brief list of these exploration attempts, but the most important one is actually, let me go back up. In 2009, they did a study, which is what was called La Crosse or El Crosse, and they actually shot a dying satellite to the permanently shadowed crater, one of the shadowed craters in the moon, and they, as it slammed down, there was a big plume of material coming up, and they made a measurement of the water, and they identified that there, in that area, there was 5.6 plus minus 2.6, or roughly 6% plus minus 3% water trapped in the icy soil. That's substantial. I mean, 6% is quite a bit of water that we can actually think about and mine. So there has been a lot of discussions about how to mine it, maybe we can evaporate it and capture it and so on. And these are some of the activities and discussions, and we'll get to that later. This is the map of the south pole of the moon, and you can essentially see the dark blues are the cold trap, or areas in the permanently shadowed crater or permanently shadowed regions that the water has been absorbed into the soil, so it's there. And there are other evidences that has been essentially measured. Also on the moon, we're talking about harnessing and extracting some of the soil and using some sort of a resin to make tiles. And these tiles, as you can see here, would be the road base or maybe can be used for the launch pads to prevent dust from rising. So there are some other plans for using the material of the moon for other purposes. One of them is what you see here as a tile. Now, Mars, of course, is a little bit further out. We haven't been able to actually land a man on the Mars, but there are several vehicles that have been, sent to Mars, and they landed, and they've sent a lot of pictures. What we know from Mars, again, different sensors and different missions that has been essentially sent out. First, initially by telescopes, and ultimately by robots like Sojourner that was sent to Mars, and Curiosity, and so on. We have made some measurements. Now, the measurements also suggest that there are cold region on both poles of the Mars, and of course there are some resources, especially water, which is again the source of energy and fuel, because once you have water and do the hydrolysis, you can get oxygen and hydrogen and use it in the engines, like fuel cell engines for getting energy back or driving your vehicles, or for certain type of rockets that can land or move around. So there are several maps that have been developed, as you can see here, and it shows the different depth of the material and the type of ice that has been deposited in certain regions. Again, if you look at the maps and the landing sites, even the pictures show something that could very well be the ice. And there has been some further studies there. So these are the location of some of the sensory systems and measurements that were made on Mars. And again, as you can see, these spots do show some signs of white material, which at this stage has been interpreted to be ice that is accumulated under the surface dust. So essentially there is deep sheets of ice and covered by the dust on the Mars. Again, some more information about different missions to the Mars, the landing sites, and pictures of what the surface would look like. And there are different depth of dust or regolith that has been measured. One other feature that has been observed on Mars is actually the glaciers on the Mars. The same as we have the glaciers in Iceland or North Pole or South Pole, when the ice is moving, there are recorded glaciers on the Mars as well. And the very likely scenario is that it is either ice or could also be liquid CO2 or carbon dioxide. These are some pictures, and it shows even a sort of a seasonal behavior on site, and again, signs of little snow. So if there are sheets of ice on Mars, one of the methods that can be extracted is essentially by borehole mining, meaning that you drill into it, create a source of heat, and melt it and suck it back into the tanks on the machine and move it to the base. So there has been some work on these concepts. So there are different water sources on Mars, and on top of that, there are some so-called hydrated minerals. As you can see, there are carbonates, silicates, and sulfate and sulfides, and also clay and clay that is rich with magnesium and iron that has also been recorded. These are some of the details. Again, I don't want to go to the details for Mars. The third area for mining, or at least target for mining, is the asteroids. Now, again, the thing about the asteroids is that, you know, for Moon and Mars, they have to go to them. For asteroid, it's very likely that they come to us, right? Asteroids are always flying, and there is a lot of them out there, and they come near the Earth and pass by. So if we can log them and, you know, try to contact them, you might be able to actually exploit the asteroids. So there are different sizes of asteroids that are orbiting Earth, and they're flying through solar system. There are typically three types of, you know, materials. It could be carbonaceous, it could be metal rich or metallic, watery or ice in some cases, and some of them are just rock. U.S. Geological Survey and NASA together have had this project where they try to log all the asteroids in the Earth orbit. And these are the asteroids that have been logged. Of course, they started with the big ones over 1 kilometer. Then the next group was 140 meters plus, and then other sizes that they could identify. And of course, you know, you see the numbers staggering. And at this stage, we pretty much have completed about 95% of the asteroids in the solar system that are over 1 kilometer. So there are all sizes and shapes, and there are also some satellite missions that have tried to identify these asteroids and, you know, look at their material composition and whatnot. Again, there are different, you know, size and, you know, location and trajectory of these asteroids. And the key difficulty is to sense it and be able to actually send a satellite in their pathway or trajectory and try to intercept it. Again, part of the difficulty is the speed of these asteroids is huge. We're talking about several thousand kilometers per hour is the speed of these asteroids. And by the time you identify it, you have to accelerate and then go very near the asteroids and try to attach and take samples. One of the problems there is the fact that they have made some calculations, and you know, if you have a orbital device, a satellite moving towards an asteroid, and let's say they're trying to attach themselves or land on the asteroid, but because there is no gravity, if you hit the asteroid with a 20 centimeter or 200 millimeters, I mean, 200 millimeters is nothing. If you hit the asteroid with a 200 millimeter per second speed, the satellite would bounce off. So it's very difficult to reach that speed and gently attach the vehicle to the asteroid and try to take samples and also try to exploit. What we know about the asteroid are the information from them, the asteroid hitting the Earth's space, and those that can survive come down or as meteorite, or you know, on the surface of the moon or elsewhere that they have hit and, you know, exploded, and we could actually do a material characterization. The scheme or the plan for asteroid is to see if you can capture one and then, you know, attach it to a production system of some sort and try to extract the material out of it, and, you know, have the raw material, you know, prepared by these activities and essentially extraction units. So we talked about all three types of resources on the moon, on Mars, and asteroid. Now let me go back and focus on the moon again, because this is the area of immediate interest. So the first target for space mining that's definitive, and we're developing plans for it, is of course the moon. But to go to the moon and actually try to take material out, you have to have a vehicle, a reliable system that can go back and forth. Therefore, development of these new rockets, the cryogenic, evolved stage rockets, are pretty critical because they are the workhorse that connect the surface of the moon to maybe the gateway and enables the landing and lifting off from the surface of the moon. So there has been a lot of activities there and developing these rockets. But when we go onto a job site, it's not like we're going to just land and start mining. You have to establish a base. You have to establish some sort of a construction activity to to have the components of your mining operations there. I mean, it's like mining anywhere on the earth. You have to establish your base camp, then mine the material, bring it to the processing plant, take the raw material, out and sort it out. And then you have to have the mechanic shops. You have to have all the other infrastructure for it. So it requires a lot of construction. So for construction, we need to dig a lot of soil and even frozen soil. We have to dig a lot of trenches to protect the utilities. You need to construct a lot of construction material to build, the structures that we want. We need to construct launch pads and, of course, assemble some buildings, which at this stage, we're thinking about modular building that can be assembled together. We have to have all types of storages and so on. So for these, we need a lot of work, and you can essentially see some of these view graph showing what the plans are. As I said, the water is in the permanently shadowed craters. So these are the deep craters. The rim of the crater has sunlight, meaning the source of energy. But inside the crater is where the water is trapped in soil, and we need to extract it. So the plan was to essentially go on the edge of one of these craters and set up a base, right? And then be able to access the permanently shadowed areas for the water. So again, movement on the moon on the surface is an issue of at the beginning you don't have roads, so you have to have pretty flexible vehicles to be able to go around. And you can see some of the examples of the rovers, surface rovers, that have been proposed for moving around and for essentially carrying out the work. Different type of excavation has to happen. Of course, excavation of the frozen soil that has, water in it, excavation of some soil for production of oxygen, landing pads, blast protection berms around the landing pads, electric cable trenches, utility roads, foundation and leveling for building the base. Of course, trenches to put the habitats underground, like cut and cover, tunneling, and of course, adding some material on top of the structure for radiation shielding. So these are some artistic rendering of what the initial base would look like, right? These are the landing pads or lift-off, areas, and these are the berms around it. That you can imagine, there is a lot of construction and excavation is involved. The habitats where people live should be buried under, a layer of regolith. As I said, it's like the cut and cover operation. The cover has two functions. One is to protect against the radiation, and second is to protect against the impact, and we'll discuss it. So this is again an artistic rendering of a job site. There has been some studies on how much excavation we need for what type of activities, including mining, and these are the estimated type of excavation and the volume of excavation in different years. Of course, this was back in 2010. Now the whole schedule is shifted by about 10 years. So for a lot of these excavation, we needed a efficient system that could be lightweight and very efficient in terms of using minimum energy to excavate the maximum amount of material. one of the approaches for, mining activities and in general construction activities up on the moon is to use a swarm of robots. And what you see here, one of the companies that's very active in this area is called Off-World. They're proposing to use a main chassis, right? The same robot, but adding different components to it so that the same robot can do multifunction. They could actually be mining, they could be putting, ground support on, they could be transporting material around, doing repairs and all of that. The chassis is the same, so the number of parts you need is limited, but you can actually add certain attachment to the unit that can do the work. So the system that we need for mining up there, it should be really mobile, very quickly moving, and very lightweight, low power and efficient. It should be automated and require minimum intervention by men, and also have to be low maintenance. Now, working on the moon is not easy. It is by any means very, very difficult because of these reasons. First of all, you don't have an atmosphere, so there is no liquid, there is no air in the area, and it's vacuum. Therefore, people cannot work, and the vacuum impacts a lot of the equipments. Radiation is very high on the surface of the moon, and it could interfere with human health. As a matter of fact, being exposed to maybe a couple of hours of this radiation is like lifelong getting exposed to direct sunlight, which is really harmful to human, and it could create cancer, cause cancer and other diseases and dysfunctions. So radiation is difficult, and also radiation interferes with the electronic devices as well. The temperature changes from minus 180 to 120 or 30 or even more degrees Celsius. So day and night, or sunlight and without the sunlight, you have such a huge swing in temperature. We don't have that on Earth. I mean, the temperature difference on Earth is typically very limited anyway because of the liquid and fluids that are air and water that would essentially balance the temperature. Gravity is low for mining equipment. That's very important because, again, you don't have the traction. Potential for impact by meteorites. Again, on the Earth, the meteorites come into the atmosphere and get burned. On the moon, that's not the case. They will come in and hit the equipment at full force, or the individuals, and can definitely damage and kill the people. There is no cooling or flushing medium on Earth. For many of our activities, we use water or air for cooling. That is not there. Dust suspension is a major issue in the Apollo missions. Whenever the dust got suspended in the air, it remains suspended for a long time. So it's an issue of visibility, and it's also the issue of dust getting into the equipment. Limited source of power. You don't have all the powers available. Difficulty of repair and maintenance. Cost of actually sending material over to the moon, and of course, no atmosphere. So also for excavation, in particular for mining activities, the problem is that it takes the same amount of force to penetrate the soil or frozen soil or rock as it would on the Earth. However, you don't have the forces because of the lack of gravity. And if you assume a 20% friction between the track and the soil, you can imagine the machine that can put 1 ton of force for cutting on the moon. The machine itself has to be 20 ton. And remember, it's about $100,000 per kilo to move a machine from Earth to the moon. And you can imagine how expensive or difficult that would be. Geology of the surface, of course, the base geology is volcanic rocks such as basalt, which is the base rock. But surface of the moon is covered by its dust or soil that's called regolith. It's very fine, and we have limited amount of sample, and with the samples we have shows that the mineral composition is like basalt, but very fine powders. We have analyzed a lot of this, soil, not that we have a lot of it, but we have done a lot of analysis on it. And for testing, we have made something that's equivalent to it. So for drilling and exploration, in any mining activities, you have to take course, or there has been a lot of work in putting different drill units together for, exploration. You can see some examples here and some of the robots that have been essentially deployed recently to be able to make an incision into the surface and take samples. Again, you can see some of the graphs here. So there has been a limited exploration there, and we're going to do some more of that right now. Again, you can see the drill bits are different than what we typically use. They are self-propelling, and also they use auger for taking the material out because there is no flushing medium. When we get to excavation part of it, there has been some artistic rendering, as you can see, how to, mine or remove soil. But this is just for the fluffiest stuff, for this loose soil at the top or at the surface of the moon. When you go to compacted material or frozen soil, none of this equipment can work. So you have to develop a different system for excavating the material and moving it. So one of the projects we worked on about 10 years ago was to use a concept of a, road milling machine, something like this, which we use on Earth to excavate the material, maybe take a layer of frozen soil or compacted soil for, mining purposes. Well, of course, one of the issues with this machine is that for cutting every type of material efficiently, you have to have a different cutter head. So, that's one of the operational challenges, meaning that you have to have different type of cutter heads. That's not feasible. So we decided to make a cutter head that can actually change this configuration depending on the type of material. So this is a schematic of what I was talking about earlier. In order to deliver 1 ton of lateral force for excavation, the machine mass should be about 20 tons. And that is relatively difficult to do for sending a 20-ton machine over to the moon. Of course, a frozen soil, as you can imagine, is no longer a soil. It behaves like rock. This graph shows, the water content versus the strength. And of course, the type of material, whether it's in clay, sand, or gravel, and the strength of the material relative to the temperature. However, most of the studies we have done on the Earth is in permafrost areas, let's say near, cold regions, top of the mountain or poles, but they're all in the range of, let's say, most of them 0 to minus 50 degrees Celsius. When we go to cooler temperatures, we don't know much about it. So we had to essentially run some tests. For our studies and a lot of others in this area, we have to characterize the frozen soil because that's the prime target for excavation. So in our studies in 2006 to 2010, we did a lot of testing of frozen simulant. Simulant is the material that simulates the regolith. And we did a lot of testing to characterize it, and then we did some full-scale cutting tests. So this is a picture of the sample that is frozen to minus 190 degrees Celsius of ice and that soil, the regular simulant. As you can see, when it fails, it pretty much behaves like rock. And the strength of it is very close to rock as well. So we did some testing to characterize it and found an analog sample or limestone that could sort of offer the same behavior as this frozen soil, right? So these are the testing. We did a lot of measurement in frozen soil and looked at the specific energy, excavated volume, and so on. And we came up with an analog, which was a limestone, to run the rest of the cutting test in the room temperature. In the course of our studies to look at the excavation, you cannot use drill and blast in the normal way, so you have to go mechanized. So we thought, let's come up with a machine that, like the one that I showed you, and see how it can mine the frozen soil. So we started with what's called linear cutting. So essentially breaking the material in lines and measuring forces. So that was the first stage of our testing. Then we did a rotary cutting test, essentially trying to develop a drum and then mine the surface. As you can see here, we did that testing, the second level of testing as well, right? And ultimately, again, these are some pictures of the surface conditions of this limestone, when it was cut by different type of cutting tools. This is a schematic of a cutter head we developed and suggested to actually be used on the surface miner. And the beauty of this system is that it has the cutters on a series of plates, and it can actually expand and contract and change the spacing depending on how the material hardness is. Or in a way, when we mine frozen soil, for water, if it has more water and the temperature is lower, the material is going to be much harder. So the cutting head has to adjust itself. So we actually made a prototype full-scale cutter head. This is the prototype cutter head, as you can see. This is fully expanded cutter head for softer material, low temperatures and low water content. And the same unit can be modified, and with small changes, it would compact. And as you can see, the spacing are much smaller here, meaning that it can cut harder material. So this is the concept of a cutter head that can adjust based on the material hardness. And of course, the cover is to prevent dust from getting into the interior of the machine. We did some full-scale testing with this unit and essentially did some estimates. So you can see the two configuration of the cutter head in expanded mode and in contracted mode. A lot of full-scale testing, and essentially we proved the concept and did some estimate based on the anticipated compressive strength of the material and how much a 10 kilowatt machine can actually produce. What you see as far as production rate is very low. Don't be surprised, because the material consumption in the earliest stage of space mining, the material you're producing, production rate is very low anyway. So what you see here is essentially trying to produce about 10 ton per day with a 10 kilowatt motor. So that was it. And the follow-up was to essentially put the machine on a chariot and, mount this cutter head up front, load the conveyor, load these boxes, and the boxes could be essentially sent for processing to a different unit. The recent project that we are involved with is about the exploration, and this is again a funded project by NASA. In this project, what we are trying to do is to actually drill into the sample, right? And while we are drilling, we can monitor the parameters of the drill and anticipate the compressive strength of the material. And in a way, we're trying to create a real-time exploration system where the drill goes to the site, drills down, right? And as it is drilling, it can measure the strength of the material, and therefore it can measure the water content. That's for exploration. Because alternatively, if you don't want to do that, you have to essentially take samples, bring it to the lab and test it. So that's our current project. It is actually coming to an end in January 2021, but we are looking for some follow-up funds to actually improve it. What we have done is we made the drill. We did a lot of drilling in analog material or concrete blocks, and also frozen material. And we have developed the artificial intelligence and machine learning algorithms that can take the information and correlate it with the material strength. And from there, we can actually see how much water is in the group. In order to design our unit, we looked at all the drills that have been deployed recently by NASA. These are different drills, the Crooks, Icebreaker, LIDA, and RPD. And our drill is very close in the specification to these drills. We have already fabricated the machine and run some tests. And hopefully in another day, another time, if there is interest, I might be able to present the results of this study, which is essentially allowing us to drill into the material and identify the layers and estimate their strength and water content. So with that, I would like to thank you for your time. And if you have any questions, I'll be glad to answer your questions.
Well, thank you very much, Mr. Rostami.